welcome you all to this video lesson in Markov Chains. We'll try and give an introduction to what Markov Chains are, and we'll proceed to discuss a few examples as well, discussing the classification of various states in a Markov chain. Before understanding Markov chain, it is essential to understand what a stochastic process is. The stochastic process is a mathematical model that describes how a system changes over time in a probabilistic way. It's a collection of random variables that are injected by a parameter, which is most often known as time. To give a very simple example, we will consider the example of a person who's on the road taking a walk. The person has two choices, either to turn left or right with equal probabilities. You may either choose to turn left or right with 0.5 probability. Since both directions have the same probability, the walk is totally random. No side is preferred over the other. So in this case, the position of the person, which changes as a function of the time, can be considered as a random process. This is going to change based on the time taken. The parameter that indexes the position is time for most stochastic processes. On your screen is an image which describes the position of the person that I showed a couple of screens back. I've generated a completely random walk independent of how this happens. So when I simulated this across 50 steps, the position of the person has varied in quite a random manner, and I've captured that for you. Now, Markov chains are also stochastic processes in which the occurrence of a future state depends only on the immediate preceding state. So this is where it differs from stochastic process. Both are based on time, but the Markov process, the current state depends on the immediate previous state, or the future state depends on the current state. So if T0, T1, T2, and Tn, etc., the time instances, and x1, x2, xn denote the various states in the given Markov process, then this process is said to be Markovian, or is said to follow the Markov process if the state of reaching the state xn at time tn depends only on whether you have already reached state xn minus 1 at time tn minus 1. So the dependence is only on the immediate previous state and none of the other states which happen before n minus 1. The Markov models like these can be used to analyze the behavior of queues in public system. We all know how queues work. For example, in this image, I consider a queue of 15 to 16 people and I focus on two people, A and B. Now, both A and B wait the same amount of time as the preceding 11 people wait in the queue. I've marked those 11 people by the red double-headed arrow colored in red. They both wait for the same time. They may lose patience. They may remain cool. You know, these are various states of mind in which persons A and B can be noted. Now, B and A both wait for the same number of time, but B may start losing patience only when A takes more time than expected to complete her service when A reaches the counter. If A leaves the counter early, B will be relaxed. If A takes more time to complete her service at the counter, B may start to lose his patience. So this can be quoted as an example for a Markov chain where the time taken before A reaches the counter is not going to affect B because both of them wait for the same number of time. But the time spent by A when she moves to the counter is going to, or may be, that may be affecting the state of mind in which person B is. Other than cues, you can also identify Markovian processes in tennis if the deuce is reached when two players are playing. So a set point is avoided. A set point is awarded when two people who are tied at 40 points each gets ahead of the other by at least 2 points. So if A and B are playing and both of them have reached 40, if both of them have reached 40 each, the set point will be awarded to A only when A gets ahead by 2 points before B makes a score. If B makes a score, once again, they have reached deuce and there is no advantage. And if A makes 1 point further, A is at advantage, and A gets awarded the set point only when he scores another point before even B starts scoring. So in this, you can understand the pressure that A is facing. He'll be more relaxed if he has an advantage, and the pressure is the same when both of them are on a deuce. Similar example can be given in soccer when a penalty shootout happens. The person who strikes the goal will be under pressure depending on whether the previous person who has taken an aim at the goal has succeeded or not. If the previous person has succeeded, he may face less pressure, and if the previous person has failed, he may face more pressure. The performance of the teams in the 19 minutes prior to the penalty shootout may not have an impact on the person who's taking a shot at the penalty kick. Or to give a more popular example, I'll draw your attention to this cricket match played between the teams of India and Pakistan in 2007 T20 World Cup. The first match that they played, the match went into a tie zone when both teams scored exactly 141. So to decide the winner, there was this practice of having a bowl out, where both teams sent 5 players, and these 5 players aim at the stumps one after the other. So they take turns. The toss was won by the Pakistani captain, and he wanted India to start first. So one bowler from India aimed, followed by another bowler from Pakistan. They alternated until 5 people are supposed to complete this bowl out. I am drawing this example to discuss 3 states of mind in which the team players can be. They can be excited, they can be neutral, or they can be under pressure. Now, when the bowling started, we can observe that Team India is in a neutral state of mind because no one has an advantage over the other. Everyone has the same 5 chances before them. What happened? We saw, I can try to refresh your memory. We know that Sehwag took the first strike and he hit the stumps in the very first attempt. So you can observe that Team India is kind of excited because they have taken the lead. What followed was a bowler from Pakistan tried to hit the stumps and he failed. So when the second time an Indian bowler got a chance, you know who it was? It was Harbhajan Singh, and he also was successful at hitting the stumps. Now you can observe that Team India is completely neutral. They're not excited, they're not under pressure. They know that they are ahead and they are confident of winning the game. What followed was another chance was given to a Pakistan team bowler, and he also failed. So this meant that India team has an advantage. So you can see the excitement and the players moving around and congratulating each other because the score leads 2-0. And what happened at the end? Every one of us knows Team India scored 3 points against Pakistan, who scored nil. So India went on to win the game, and you see the excitement in the faces of the players. Now compare this with how the Pakistani fielders and the team players might have felt. Now, given that India has scored the first point, Pakistan may try to remain neutral because when you're under pressure, you may not perform well. So they try to remain neutral before they take the first chance, and you see that they fail. So there is pressure, immediate pressure on the Pakistani team players, and that is visible in their faces. Now, when India scores a second consecutive point, there is more pressure. So from neutral, they move down to pressure, and they remained at the pressure state before taking even the second strike. I'll state this again. All of this depends on the immediate previous performance. The fact that both teams scored the same number of runs, the same number of overs, does not impact the pressure. So Umar Gul takes the second strike with the score reading 2-0 and he fails. So there is more pressure on Team Pakistan and the captain, former captain Shahid Afridi gets a chance next. And before he scores, we see that India get ahead. They score 3 to Pakistan 0. And now there is evident pressure on everybody else in the Pakistan team. And you know what happened? Pakistan could not score any, and the game was awarded to India because they are ahead by 3-0. So here we see that the states of mind of the players went from neutral to pressure and pressure for Team Pakistan, and from neutral to excited, back to neutral and excited for Team India. Team India never felt the pressure because they kept performing consistently well during the bowl out, and comparatively, Team Pakistan did not do. So this can be quoted as an example for a Markov process where the state of mind of a player who's currently aiming at the stumps depends immediately, depends only on the immediate previous person who took an aim at the stumps. If he succeeds, you may be under pressure. If he has failed, you may feel neutral or you may not feel pressure at all. So this can be given as quite an interesting example for a process which is Markovian. Now, next we will try and classify the various states in the Markov process. Now, the states can be given any names. We can call them as ABC, we can call them as under pressure, neutral, or excited, or like the examples I gave you. But in general, we classify a state of a Markov chain into the following types. We call a few states as transient or recurrent. Only one of them is possible. Periodic or aperiodic, where one of them is possible again. Non-null persistent as the third state, and ergodic or non-ergodic as the fourth state. Now, based on all of this, a given Markov chain can be classified as an irreducible Markov chain. We'll look at how this happens. Now, what you have on screen is a pictorial representation of Markov chain using what is called as a digraph. A digraph, if you can recall your graph theory lessons, is a graph in which each line has a direction. Now, the states in the Markov chain, namely A, B, C, D, and E, are vertices of the graph, and the possible transition from state A to state B is indicated by an arrow mark. Now, a double arrow will mean that I can move from one state to another and vice versa, like B and E. From B, I can go to E, and from E, I can come back to B. Transition from both states to the other is possible. However, when you look at states A and C, transition is possible only in one way. I can reach state A from state C, but I cannot reach state C from state A using a direct possible way. There is an indirect way. May go from A to B to D and then to C. So this is the diagram representation of a Markov chain. We just classify some states of the Markov chain into a few types. A Markov chain is irreducible if there is a communication possible between any two states of the Markov chain. And in this graph, we see that there is a communication possible from any state to any state. Like if you start with A, you can go to B with a direct communication, to D through B, to D through B, to C through B and D, and to E through B. So from A, I can reach out to the others. Similarly, from B, I can reach E and D directly. I can reach C by reaching D, and I can reach A by reaching B and C. We can examine all of the states and we can find out that every state is reachable or every state can communicate with every other state. Therefore, this chain, this Markov chain is irreducible. The next possible classification, and I've given you another example here. Here again, we see that there is communication possible. Here, though, there is one added advantage in that there is a direct communication from state A to state A itself. Such a communication was absent in the previous state. Therefore, to reach A from A, I may have to take a very long process. A, B, B, C, A. This is one way to reach A from A, or A, B, E, B, A. This is also a way to reach A from A. Here, though, the communication is slightly different. That is the communication from A to A possible, and the communication from B to B possible. So this Markov chain can also be analyzed. I'll leave that as an exercise to you. Every state communicates with every other state. So this is also an example for an irreducible Markov chain. The next classification is about a state being transient or recurrent. A state is recurrent if it can be reached from any state that is reachable from X. For example, in this image, state C reaches out to state D, and I can also reach back to state C from state B. The same is true for state B. Therefore, C and D are recurrent. However, state B is not recurrent because B reaches out to B, but you cannot reach B from B. There is no possible transition to reach B from B. The same can be said about state A. From A, I can reach B, but I can never come back to A from B. So A and B are not recurrent. We call them as transient. C and D are in fact recurrent. The next classification, the last of them, is about a state being called as a periodic state. A period depends on the shortest possible time in which I can reach the state back after starting from the particular state. We define this using the notion of a cycle. A cycle is a graph theory concept where I start from a state and I come back to the same state. So from A, I go to B, I go to D, I go to C, and I come back to A. So this is what I call as a cycle. So using cycles, we define the period of a state. A state X is the period K if K is the greatest common divisor of the lengths of all cycles that pass through the state. For example, if you consider state A of this Markov chain, there are two cycles which pass through state A, one with length 6 and the other with length 4. I had given you the example of the length 4 cycle in the image. This cycle has length 4. The greatest common divisor of these two numbers, 4 and 6, is 2. Therefore, state A is periodic with a state 2, with a period of 2. Similarly, state B has two cycles of length 2 and 4 each. Their greatest common divisor is 2. State C has two cycles with a period of 4 and 6. So its GCD is 2. Therefore, C is periodic with state 2. The same is applicable to states D and E. So this is how we can classify a state of a Markov chain to be periodic. And now we come to the alternate representation of a Markov chain, which can also be done in the form of a transition probability matrix. So what we saw till now were representations in the form of a digraph. They can also be represented using matrices. The rows and columns can be labeled by giving the names of the states, and the probability by which the transition happens from one state to another can be the entry of the particular cell in the matrix. So from this example, we can consider the directed graph here. I can move A from A to B with a probability of 1, and that is being indicated by this number here. And from B to A, I can move with a probability of half. B to C is half again. C to B is 1, and these are the four possible transitions. The various rules for defining a transition probability matrix is that the total of all entries in any row of the matrix must be 1. May not bother about the columns. The column totals may vary. The row totals must be 1. In each row, the entries should add up to give you 1. And since each entry is a probability, all these entries are necessarily non-negative. So based on this, let's classify a few problems where we uh, classify the states of a given Markov chain into the types that we just saw. We are going to classify them as recurrent or transient, periodic or aperiodic, ergodic or non-ergodic. We'll see them using these examples.
Yes, there is a direct communication from state A to state B, and from A to B and C, and to A to B to C, and then to B and then to A. So from state A, I can reach out to every other state. This is represented by these three equations. The same is true for state B. From B, I can reach out to A and C with probabilities of half. And once I have reached C, I can always come back to B with a probability of 1. Likewise, if we explore C, we see that from C I can reach out to B. And once I reach out to B, I can reach out to A also. And having reached B, I can also come back to C. So here we observe that from every state, we can communicate with every other state. Therefore, this entire Markov chain is in fact irreducible. Next, we discuss the transient and recurrent states of this Markov chain. A is recurrent because A reaches out to only B, and from B it can always come back to A. B is recurrent because B reaches out to only A and C, and having reached A, it can come back to B. The same is true with C also. C is also recurrent because C communicates only with B, and having reached B, it can always come back to C. So all the states of this Markov chain are in fact recurrent. Now let's count the number of cycles that pass through each state, and let's find out the period in each case. There are two cycles which pass through A, namely ABA of length 2 and ABCBA of length 4. The period of the corresponding state will be the greatest common divisor of 2 and 4, which is 2. Therefore, state A is periodic and it is not aperiodic. Similarly, there are two cycles which pass through the state B. We see that each of them has a length 2. So the period is the GCD of these two lengths, which is 2 again. So we conclude that state B is periodic and hence it is not aperiodic. C again has two cycles passing through it. One of it has a length 2 and the other has a length 4. Therefore, the period of the state C will be GCD of 2 and 4, which is 2. So state C is also periodic and therefore it is not periodic. Now let's consider a different example to discuss the periodic nature of the various states. We see that A reaches out to itself in a cycle whose length is 1 because no other state reaches out to A. There is only one communication from A initiated by A, and that is to itself. So the only cycle that you can think of is A to itself, which is having a length of 1. Similarly, from D, I can reach out only to itself because D doesn't reach out to any other cycle. So D has a length of only, has a cycle whose length is only 1. But B and C are not same. B reaches out to C and the reverse also happens. So B to C and C to B has a length of 2 and B to B itself has a length of 1. The greatest common divisor though will be GCD of 1 comma 2, which is 1 again. And then talking about the state C, we see that C has two cycles which pass through itself. I can reach out from C to B and then back to C in a cycle of length 2. And there is always a communication from C to itself, which has a length of 1. So therefore, the period of C would be GCD of 1 and 2, which is 1. What is interesting to note here is that the diagonal entries of this matrix are non-zero, and that causes us to observe that the period of each of this state is certainly 1. So this leads to the conclusion that each of the state in this Markov chain is not periodic, they are aperiodic. And there is another easy way to understand this. Whenever there is a diagonal entry which is non-zero, the corresponding state will definitely be aperiodic. So we have 1 comma 1 to be 1 by 4. Second row and second column is 1 by 3. Third row, third column is 1 by 4. The fourth row, fourth column is also non-zero. Hence, each of these four states is not periodic, they are aperiodic. Next, we classify a state to be trapping or observing if it is not accessible from any other state in the Markov chain. This is identified by having a diagonal entry which is exactly 1. This will lead to the state where every other entry in the corresponding row is a 0. Such a state is called as a trapping state or an observing state. For example, we see that the state A here is trapping because the diagonal at 1 comma 1 is exactly 1, which means every other entry in the same row will be 0. Therefore, we can never reach state A from any other state, which is B or C. And hence, we conclude that A is trapping or absorbing. The next classification is about the states of a Markov chain when we call them as non-null persistent. All states are non-null persistent in the Markov chain if the Markov chain is finite and irreducible. For example, we consider this Markov chain. This state is definitely finite because there are only a finite number of states here. And we already showed a few slides back that every state can communicate with every other state here. So the entire Markov chain is irreducible and therefore all of its states are non-null persistent. The next classification is of a state being ergodic. A state X is ergodic if it is non-null persistent and also aperiodic. So having already learned what these two terms, aperiodic and non-null persistent, mean, we can clearly classify a state to be ergodic. For example, let's get back to this Markov chain. It is definitely finite because there are a finite number of states in it. And of course, it is irreducible. We can reach out to from any state to every other state. From A to B, there is a direct communication. And from A to C, we can also go because from B, there is a communication to C. B to A is possible through C. C to A, there is a direct communication. So this is an irreducible Markov chain and also finite. Therefore, all states are non-null persistent. We just take some time calculating the periods of each of its state. There is the cycles through the state A. We see that there is one cycle whose length is of 3. So from A to B to C and then to A, we have a length of 3. So state A is periodic. And when you look at B, there are two cycles. One from B to C and then back to B with a length of 2. And the other from B to C to A and then back to B, the length of 3. But the greatest common divisor of these two lengths is only 1. Therefore, its period is 1. Therefore, B is not periodic because its period is not greater than 1. So we already showed that B is non-null persistent, and because it is also aperiodic, we can conclude that the state B is ergodic. Likewise, when you look at state C, we see that there are two cycles passing through C, one of length 2, the other of length 3. So there, the period of this state will be the GCD of the two lengths 2 and 3, which is again 1. Therefore, C is not periodic. And we have already shown that all states of the Markov chain are non-null persistent. Therefore, the entire state C is in fact ergodic. So we have classified a state of a Markov chain into many types. We have seen that it can be transient, it can be recurrent, it can be periodic, it can be non-periodic, it can be non-null persistent, it can be trapping or absorbing, and it can also be ergodic. And overall, we have also classified a Markov chain to be an irreducible Markov chain or an aperiodic Markov chain. I'll follow this video lesson with more problems on classifying these states of a Markov chain very shortly. Thank you.